Okay, off we go. So last time we were talking about how to basically extend this previous idea we had of a Riemann sum. Here is our single variable, I might say single index because there's a single index I that goes from 1 to n. Single index Riemann sum. This is the basis of the idea of a single variable integral. And the big picture is, look, sometimes you have stuff that you distribute over an interval. You want to break that interval up into a bunch of little pieces. Whatever it is that you're interested in, you'll identify on each individual piece and then add up over the whole interval. Right, so that's just broad strokes. That's the big idea. So a 2-index Riemann sum that we wrote down next, same basic idea. Same basic idea is that, well, we've got now a 2-dimensional region. We're going to start with rectangles, just to keep life simple to get started. And how are we going to handle some quantity that's distributed over this rectangle? Well, we're going to break up the rectangle. Not an interval this time. Now we're going to break up the rectangle into little pieces. We're going to understand what we're interested in on each piece. Whereas over here, we maybe understood, let's say, mass per unit length as, we understood mass as mass per unit length times length. Over here, when mass is distributed over an area, we're going to understand mass as being mass per unit area times area. Same basic idea, just now area instead of length. Understanding the quantity in question on each little piece, and then again adding up over all of the pieces. Now, to add up over all the pieces, things are a little bit different. We only had 1 index worths of pieces over here to add up, so we only need 1 index, and the summation I goes from 1 to n. Here we've got pieces kind of in 2 different directions. There's I keeping track of where we are this way, j keeping track of where we are that way, so both I and j have to go from 1 to n to actually add this all up. Okay, details as to the formulas, and that's all stuff that y'all can think through. Half of this, of course, you saw in Calc 1. The other half is totally analogous. But basically the same sort of strategy of construction. This is where we ended last time, and this is our motivation for a new kind of integral. This exact expression here is going to be our definition of a double integral. We're going to use this notation, 2 integral symbols instead of 1, just to emphasize that this is a 2-dimensional domain. We have 2 indices keeping track of where we are. We have a 2-dimensional notion of size. We're no longer interested in lengths of subintervals. Now we're interested in areas of sub-rectangles. Right? So that's the 2 integral symbols, and I think the rest of the notation is pretty believable. This is suggestive of pieces of area, which is what that represents on the right side, and this again is just kind of a shorthand representing that we're doing a limit of a summation in kind of the usual way. Okay. All right. Now, one thing to keep in mind. Don't misunderstand what we're saying here. I'm not saying that a double integral is something that you should think of some other way and this is how you would compute it. Absolutely not. It's quite different from that. I'm saying this is something we're going to be interested in computing. We're interested in computing 2-index Riemann sums. That's our object of interest. And this is just a shorthand notation and convenient terminology. Because there's a lot to write down here, and it gets a little clunky sometimes, and we don't want to write that down all the time. All right? So Riemann sums are what we're interested in. Okay. All right. Is everybody on board? So, real quick side note, our book, I really like our book. It, however, was not written tailor-made for this course. It is a little bit of a higher cut through the material than is really sort of what Math219 is about. So there's going to be stuff here and there that is, you can just kind of ignore or don't sweat too much anyway. So there are more sophisticated versions of this definition. These more sophisticated definitions are important in circumstances that we're not going to encounter in this class, right? We're going to pretty much exclusively be interested in functions that are either continuous or at least piecewise continuous. And for piecewise continuous functions, all the extra stuff that the book does about irregular partitions and test points doesn't actually make any difference. It can be helpful to prove certain theorems. We're not going to be proving those certain theorems. So it's just not going to be our thing. So where the book uses that stuff, just kind of, I would say, just ignore that. That's irrelevant for our purposes. Okay, so let's do one. Let's see our very first double integral in action. This is going to be a problem we've talked about before. We've previously talked about looking at a graph and specifically looking for the volume under that graph sitting over a certain rectangle. And we already have an answer to this question, so it's a pretty reasonable gripe you could make. Why are we revisiting a question to which we already have an answer? And I've got a really good answer to why we're doing this, and I'm going to keep that withheld for just a moment. But let's go ahead and do this anyway, and then I'll reveal why we care. We've got our domain, and I'm going to chop up our domain into little pieces. That's what the two-index Riemann sum does, right? We take our domain, we chop it up into little pieces. I'm going to argue that on each little piece, the amount of volume under our surface sitting over each little subrectangle, that's actually an easy problem. The volume of that little French fry, right, is height times the area of the base. No big deal. Is that cool? And so, okay, wait a minute. We want to compute the entire, like what's the total volume of this whole biggie fries here? Well, we just add up over the entire rectangle. Now, where do we get to the part where we actually compute and get an answer? Yeah, we're not going to, that's not going to be our goal here. There's not a good way to do that immediately, given how we've got things set up right now. My point here is that by taking this approach, notice that what we get is exactly a double integral. So whether we can compute it or not, a double integral is a perfectly reasonable way to represent the answer to this question of what's the total volume under that graph. A different approach than iterated integrals gave us. How we doing? Is everybody with me? All right, here's why we care. Why did we try to solve a problem that we already knew the answer to? And it's going to come down to this diagram right here. Let me remind you first of the things that we've already done. What we did, the very first thing we did in this chapter is we considered the question of, volume under a surface, volume under a graph. We did it with an iterated integral. We talked about how you can compute iterated integrals, and you got to pay attention to which variable is a constant and which variable is a variable and at which stage of the calculation, blah, blah, blah. Fine. We already did all that stuff. We've got this new construction now called a double integral that has this nice feature that, and we're going to see some of these applications momentarily. This double integral is a construction that we're at least optimistic at this point will allow us to denote how to compute a bunch of different application problems. And again, examples incoming. Okay, so double integrals connect to applications. Iterated integrals help us compute volume specifically and only. Right, and let me just remind you, you can't, all right, we tried and failed. I mean, you can make it work if you're willing to put in a bunch of effort. No, but you don't want to do this. But basically failed in trying to take, let's say, mass and immediately write it down as an iterated integral. The units don't fit together. It just kind of doesn't work. And likewise, you can't just assert that mass is volume. It doesn't make any sense. It's a baseless assertion. Okay, so this is where we were at as of a few moments ago, what we can do and what we can't do. So why did we spend time talking about how to compute volume with a double integral? Well, it's because with the fact that we have now an answer to the same question computed two different ways, that tells me that I can compute double integrals with iterated integrals. Everybody see what happened there? Let me clean up the picture a little bit. Get rid of all of this stuff. We had previously talked about how to compute volume with an iterated integral. We just now talked about how you can represent volume as a double integral. Two answers to the same question have to be the same answer. And now we've got the sort of the final piece of the puzzle, the way I like to think about it anyway. And here's how in practice, computational purposes, this is not, mathematician formality, abstraction, that kind of thing. If you want to solve a real world problem, the foot in the door, the thing that allows you to represent the answer to your question with math you can write down is a double integral. So step one is going to be rewrite the question with a double integral. Then we can say step two, rewrite your double integral as an iterated integral. And then step three, plug and chug your iterated integral with the fundamental theorem. So in some sense, volume, the role that volume under a graph has played in this is, on the one hand, it's a way to visualize, and that's kind of nice, I suppose. Don't buy in too much on that. It's ultimately just one of many applications, and frankly, not a particularly important one, right? The main thing that we've done with volume here is that it gave us a geometric way to see how plausible it is that double integrals and iterated integrals should give you the same values. So the point to volume is that it helps us compute double integrals. It's not that double integrals help us compute volume. Volume helps us compute double integrals. So this is our roadmap. This is how we're going to answer questions. This, by the way, is a indication of what I want to see on exams. If there's a question, compute the mass of the blah blah, or compute the amount of work it takes to whatever. I want to see all three of these steps. I'll show you an example right now. Here we go. I like mass as a first example. It's very relatable, very visceral. And here we go. We've got our domain here. This rectangular sheet. We've got mass distributed over this rectangular sheet. We've already taken one crack at trying to compute the amount of mass distributed over this rectangular sheet. Crashed and burned, right? The units didn't work out. We were talking about mass per unit area times length, and it doesn't really quite fit, right? And again, it can be done, but it's not a good idea. You don't want to go down that road. It's a pointless effort. The much easier way to do it is to argue as follows and say, look, per this roadmap, let's write the answer to our question as a double integral. How would I compute mass as a double integral? Well, I first observe that the whole is the sum of the parts. Mass is what I like to call an accumulating quantity. If you take this mass that we have here and chop it up into little pieces and look at one little piece at a time, right? The amount of mass in that little piece plus the amount of mass in that little piece plus the amount of mass, you keep adding up over all the little pieces, the whole mass is the sum of the individual pieces of mass. And that's all I'm saying here is the whole is the sum of the parts. Is that cool so far? Okay. Real quick digression. Lots of quantities have this feature that the whole is the sum of the parts. Now, I like the term accumulating quantity to describe that because, I don't know, to me that just conjures what this is saying. Very importantly, lots of quantities do not have this property. Not everything we're going to be interested in this course is an accumulating quantity. And so we're going to have to be careful to distinguish, wait a minute, which are and which are not. Okay, the mass is geometric sort of, physical appeal, right? Okay, and then you make the observation that, of course, on any given little piece, mass is at least well approximated as mass per unit area times area. That's what mass per unit area is for. That's its job, right? Mass per unit area is the thing you multiply by area to get mass. So no funny business with units and, disconnects and unit problems. It just makes perfect sense. It's perfectly reasonable. And then you notice that this is the very definition of a double integral. Okay, so this is what I'm going to call our step one. Our step one is that we rewrite our application as a double integral. That's up here, the first step in our roadmap. Everybody all right? Okay, step two. Let's see. Let's remind ourselves. Step two. We're going to try to rewrite a double integral as an iterated integral. Okay, that's actually pretty straightforward. Double integral. Here's the corresponding iterated integral. The given rectangular sheet that we know tells us the A, B, C, D that are our bounds. Right? Double integrals are rectangular integrals. Double integrals are iterated integrals. Just write that down. And then step three, plug and chug, compute. And we've talked about how to do computations, how to plug and chug. You basically just apply the fundamental theorem twice. You got to keep track of what's a constant, what's a variable, and play by the rules, of course. But that's just plug and chug. You'll notice I didn't even give a specific formula for this density function. So we don't even know what this integrand is because I didn't want to crank that out anyway. But if you knew this function of x and y, then it would be very plug and chug. Okay. All right, how are we doing so far? Everybody seeing the three-step process here? Yeah.
It seems to me like we said we can't do iterated integral for mass last session.
Yeah.
And then now we're doing it with the intermediary of going through the double integral.
Correct.
So
yes.
Technically, what has changed between then and now?
So the important distinction there is we've got to make sure to distinguish between things that are true and things that are clear. Right? We're looking to make clear reasoning. Right? We're trying to make an argument. We're not trying to get an answer. Remember, I was always talking about how this is not a class about answers; it's a class about reasoning. Right? So. Yeah, computationally, it is true that mass can be computed with an iterated integral. The question is why? Where is the clear argument by which that makes sense? And if you try to make that argument directly, that's what crashed and burned. It's not the result that's wrong, it's the reasoning that's not clear. Is that satisfying?
Yeah.
Okay. Yeah, so we have fixed that by talking about this thing called a double integral. That reasoning really is pretty clear because mass per unit area times area gives us mass, no problem. And then we've had a separate argument that allows us to go from here to here. Is that okay? So you're all happy?
Yeah.
Yeah, good deal. Okay. Great question. Good stuff. Okay, so that brings me, by the way, to the next thing I was going to say. So what is it that I want y'all to show me on an exam? I just want to be very explicit. To get full credit on a question like this, what do you have to write down? There's a lot of stuff I wrote down here that you really don't have to write down. I wrote it down as sort of expansive as reasonably could because I wanted to make sure to explain all the steps. In practice, on an exam, perfectly fine to just say mass is a double integral, which is an iterated integral, and then plug and chug with the fundamental theorem. Just hit those highlights, totally fine. Now, students very often ask me, why do I have to write that down? Right? I knew that this is where I was going to be the next step. Why do I have to write down where this came from? And again, so that you've already kind of asked the relevant question. It's the difference between right answers and valid reasoning, right? And clear reasoning. If you don't write this down, it looks like you're making this argument, and that's not a clear argument. That argument just doesn't really hold water as without lots of ugly little details being done that you definitely don't want to do. So that's why you have to write down the double integral. As soon as you write down the double integral, then your argument very clearly is what it's supposed to be. Full credit, no problem, everybody wins. Okay. All right. Now let's talk about how much this costs you. How much of an imposition is this on you? And well, the imposition is I'm just asking you to write down this one extra little thing. It'll take you 4 seconds. Right? It's not hard to write that down. You just write down this one thing, and then how you got from here to here. Now I know you're not making reference to a nonsensical argument, right? You're making a very clear reference to a perfectly valid argument. One little thing, right? Now, we've seen examples in the past where you can view it as glass half full or glass half empty. I'm going to strongly encourage y'all to view this as a glass half full here. Don't think of this as, oh man, I'm gonna lose a couple of points if I don't write this down. No. Think of it as, oh, sweet, I get a couple of points for writing down a really simple thing. Right? You write down this one thing, that's money. Points in the bank, right? Go ahead and get those points. Does everybody see what I'm talking about? Again, you can view this in a glass half full kind of sense. Any questions about any of that? Okay. All right. Okay, let me talk about notation a little bit. So you'll notice this business down here, sort of a different way to write down, ultimately kind of morally the same argument here. You've noticed up here, I'm sure, that this smacks of that, and this smacks of that, and this smacks of that, right? I mean, the notation is strongly suggestive. And the take that we're going to apply here is that, look, if we're eventually going to turn if we're eventually going to turn this into that anyway, we're eventually going to turn this into that anyway, why not let's just go ahead and do that from the get-go. It's just notation, and it'll be understood that this is what we meant when we write these things individually. And this is actually a very common practice, and it does make it a little easier to write things down. So for example, instead of literally saying mass is the mass of the whole is the sum of the masses of the parts, I'll just write it like this. Again, that's eventually going to turn into a double integral symbol anyway. Why not just write it down like this in the first place? It's a little bit easier, a little bit less to write down. Technically, we haven't defined what we mean by this, right? M is not an axis. There is no M axis. It's really not, I haven't in fact defined this. But again, if you're comfortable with this little sloppiness of notation, it's clear that what we mean by this is that. So very common. I encourage this. Perfectly reasonable. And so instead of writing down that, you can instead write down that, and it's just a little cleaner on the page. Let me give you another example where this can be particularly handy. This is, there's a lot of details in this example. We're not going to go through all the details. I'm going to go through the setup, and I'm going to go through the part that it really motivates the example, which is this use of that integral shorthand. That's what we're going to be most interested in. And then I'm going to leave it to y'all to punch up the plug and chug. So, okay, what's going on here? We're going to build a 6 foot tall, 10 foot wide wall made up out of materials that are currently sitting on the ground. A bunch of bricks sitting there on the ground. And, well, there's a lot to do when you build a brick wall, right? Among other things, all the bricks that will eventually make up your wall, they're on the ground, and somebody's got to bend over and pick them up and lift them up to whatever height where they go in the wall. And that adds up to a lot of work. Bricks are heavy, right? There's a lot of them, and you're some of them you're picking up as high as 6 feet. That's non-trivial, right? That's a lot of work. Literally, in a physics sense, work. So, how much work is it? Reasonable question. And I argue as follows. First of all, I can talk about how much work does it take to lift one single particular brick up to the height where it's going to go. That one little single particular brick. And then I argue, and I think this is very reasonable, the total amount of work is what you get when you add up all those little pieces of work. Physical appeal. Does that make sense to everybody? Right, the grand total amount of lifting work is the sum of the amount of lifting work of each individual piece. Okay. Notice I'm using integral shorthand. Right? I could write that as a Riemann sum. It's easier to write this as a convenient shorthand. Okay. All right. Then I say, okay, well, here was where the brick was in the first place, and that brick weighs a certain amount. By the way, keep in mind that weight, right, is a force. It's not to be confused with mass. Mass is not a force. Mass times acceleration is a force. Right. So in order to avoid that little issue, everything in this question is going to be about weight, such as pounds. Right. People commonly conflate mass with pounds. Pounds is force, not mass. Anyway, we're going to avoid that problem entirely by dealing just with forces. Forces are what we need anyway, so we don't have to deal with G, the multiplying by gravitational accelerator. That's factored into the problem. So I've got a brick that has a certain amount of weight, and I need to lift it a certain distance from where it is on the ground, where y is 0. And I need to lift it up to where it's eventually going to be, x comma y, which means I need to lift it a distance y. And so what I have here, this equation right here, just says work is force times distance. And that allows me to turn one integral shorthand Riemann sum into now a new integral shorthand Riemann sum. Just convenient shorthand. How are we doing? Is everybody with me? All right. Okay, next. All right, so this brick that's sitting here at ground level, how much does that brick weigh? Well, we have this density given to us. It says here density is this function. What I didn't write down, what's I'm going to say suggested by context, is that because the weight is distributed over an area, this is force per unit area. And force then is force per unit area times the area that brick will take up on the wall. And so again, now I've again rewritten what had been an integral shorthand of a Riemann sum into now another integral shorthand of a Riemann sum. Oh wait, this one's actually literally a double integral. Right? So anyway, the punchline, this integral shorthand made it relatively easy to write down how I developed the question, the work question, into a double integral. So this is what I would call phase one of this problem. And then, let's see, I've forgotten the colors I used. Turning that into an iterated integral is phase two. And then plug and chug, phase three. And y'all can look at those details on your own. Again, my motivation was to talk about phase one there. How we doing? Everybody okay with this? Okay, so next thing, we're going to move on and talk about a very significant question. What if the domain's not a rectangle? This is a very reasonable question. Sometimes you build walls that aren't rectangular shaped. Sometimes mass is distributed over regions that are not rectangular shaped. Sometimes populations are distributed over states that are neither Wyoming nor Colorado. Right? What if we want to compute the population of Wyoming, that's fine, and we've got the tool to do it at this point. But if you want to compute the population of North Carolina, well, that's not a rectangle, and we don't have the tool. Okay, so how do we do this? It turns out it's surprisingly straightforward. There's a lot of formalities, and I'm going to totally skip. Not our problem, not what we're interested in. But let's just go straight to an iterated integral. Again, let's answer the volume question. How much volume is there under a graph? And we're going to do almost exactly the same argument. The whole volume of the entire loaf of bread is the sum of the volumes of all of the slices of bread. Doesn't matter if the base is a rectangle or not. The loaf is the sum of the slices. Just the same as before, the volume of an individual slice is going to be the cross-sectional area times the thickness, just like before. That cross-sectional area that we're interested in is still going to be the area under a curve. That curve is still a partial function. It's the graph of the partial function. The area is therefore still an integral of that partial function. Everything's the same. Practically everything's the same. There's one minor detail that's different. But big picture, it's so much the same. Before we get into the differences, everybody see how what we're doing here is very, very similar. We do almost all exactly the same stuff. So here's where it gets a little different. Just a little bit, but in a very important way. For a given value of y, when I talk about the corresponding x integral, where x is going to go across like that to compute the cross-sectional area, like from there to there, we're kind of starting at that point. Said differently, there's our lower bound for x. If I have a different y, if I were to look, let's say, at this value of y instead of the one I have drawn, for that value of y, we're ranging over a different range of values of x, starting at a different point. Oh my gosh, it's hard to draw a straight line dotted. Let me cheat here. Which will give me a different lower bound for the x coordinate. That's the only difference. Yes?
We need to first check if x can be written as a local function of y, right?
There are some questions there depending on the shape of the domain, and it's not going to be our problem. Yeah, we're going to deal with that by just kind of eyeball glance looking at the geometry. But yeah, technically, and so if you want to be truly formal about it, the case could be made. Maybe you should do that, but it's not going to be our problem. Okay. Yeah.
And we're not going to deal with like a volume of something like a piece of cheese that has holes inside.
We are, but not that specifically. But that kind of thing we are going to have to deal with, but we're going to deal with it in different ways. Yeah. So I'm just going to say for the moment, let's not worry about it, and ask me again in a few weeks, and I think you'll see that we have our different methods for dealing with that. Yeah. Okay. So the big takeaway here is different y's give you different bounds for your x integral. And I claim, again, that's the only thing that's going to be different. And you can see that in action by the fact that the x bounds are literally written as functions. So this lower bound for the x integral is written as it should be, as a function of y. Different y's give you different lower bounds. And likewise, different y's give you different upper bounds. Everybody buying it so far? Okay. All right, bad news, good news. The bad news is these pictures are hard to draw. They're three-dimensional. It's harder than it looks, right? I'll give it a try. This took me a while to make it, look kind of reasonable and decent. That's the bad news. Here's the good news. You don't need to draw that picture. There's no three-dimensional picture you're going to have to draw to do a double integral. And the reason is, when you look carefully at what we've done here, and here's our domain, right? This is our new non-rectangular domain here. Notice that the relationship between, let's say, the lower bound and the input value y is entirely based on points on these edge curves, all of which is entirely in the xy plane. All we need to figure out what's changed, how are these bounds different, all of that is entirely interpretable from just looking at just the domain itself. The height doesn't affect the bounds. The height only tells you what the integrand is, and we already knew that anyway. It's a big point. Does everybody see what I'm saying there? Right? So there's no reason to draw this difficult, challenging three-dimensional picture. Just draw just the domain itself. Here it is, for example. And so let's make this sort of equivalent two-dimensional argument here for this domain. Here we go. Given a value of y, if I want to know how does the x bound, and of course this is a value of x, so this is an x bound. How does that x bound depend on y? Well, I can just see, look, that x bound is going to come from understanding this point, right? That value of y implies that my x slicing is going to start at that purple point. There's my x slicing that's going to happen. It starts at that purple point. That purple point is on this red curve. And if I can see where that purple point is, I can identify what that red curve is, then I can just solve for x. Right? This lower bound I'm interested in for x. That's a value of x. Just solve for x in the equation of this curve. And boom, we're in business. Two-dimensional picture only. Okay. So that's going to be the process. And just to sort of complete that thought, these bounds that we're interested in come from understanding certain points that identify the start of the process that are on certain curves for which you can find the equation, and then you solve for the variable that bound represents. Several examples to follow, but is everybody seeing the strategy? Okay, let's do something. Picture gets all messed up. Okay, here we go. Okay, all right, so first example. Now, this first example, we're going to start with an integral that has already come to us as a double integral. And reminder, when you're computing some quantity, some application, there's a three-step process. You got to, depending on whether you're computing mass or population or what have you, step one is to write it as a double integral. I'm going to presume that that's already been done. We want to compute this double integral because it represents something we care about, and we've already figured it to this point. Okay. Let's suppose that our domain is this triangle that has these specific vertices, given specific vertices. And now the question is going to be, how do you do phase two? How do I take this domain, namely this triangle, and turn the double integral, turn the double integral into an iterated integral? That's going to be our goal here. Does everybody see what we're trying to do? Okay. We're going to follow this process pretty much. We're going to find bounds by identifying the relevant points, seeing that they're on certain curves that have certain equations, and then solving for what we need. So here we go. All right. Now, very often the outside bounds are going to be easy and straightforward, borderline obvious. It's good to capitalize on fortunate situations when you can. If I'm looking at this region, I want to know the range of values for x. Well, look, my x slices all look kind of like that. X pretty clearly starts there, where x is pretty clearly 0. It's the origin after all. And then we're going to end, that's our last slice, where x is pretty clearly 1. Outside bounds very often are just clear by inspection of the picture. That's convenient. Where we have to rely on the method is finding the inside bound. So we're going to fix now a particular value of x. We're going to move on to asking, okay, what's the range of values of y? Well, y is going to proceed sort of like that. And let's go through our process. Here it is. If you want to understand a bound, identify the corresponding point. See what curve it's always going to be on. Write down the equation. Solve. Okay, so our lower bound for y comes from this point right there. Right, no matter what value of x you're looking at, that's what the point's going to look like that determines our lower bound for y. And it's always going to be on this curve. Now the geometry of this situation, again, those vertices were given. You could do some old Algebra 1 stuff from high school and figure what the equation of that curve is. It ends up being that curve has this equation. Keep in mind, we're trying to find a y bound. So in this equation, I need to solve for y. Sweet, right? It's already solved for y. So solving for y, there's my formula. And my lower bound for y is 0. Everybody see the process? Okay, let's do the upper bound. Okay, so again, for that value of x, looking at the y range, my ending value of y My ending value of y comes from that point, which is on that curve. Real quick, let's make the observation. How did I know that this point would always be on this curve? Picture. The picture tells me, right? Thinking about the slicing process on the picture is what allows you to distinguish which curve it is that has the point on it that determines the bound you're interested in. So you've got to have a good picture, at least a reasonably doesn't have to be beautiful, right? But a reasonably interpretable, decipherable picture that you can rely on to answer these questions for you. Okay, so bound, point, curve. Algebra 1 tells you that's the equation of that curve. Keep in mind these points were given, right? Here's where it's easy to mess up. A lot of students fumble on the 2-yard line here. It's practically in the end zone here, but wait a second. So is it y or is it x? Which is it? Is it y or is it x? Reminder, I need to solve for y. I need to think of y as being a function of x. So what I'm interested in is what is the function of x that tells me what y is. And the function of x, let's see here, I'll do this in red. The function of x that tells me what y is x. Not a y. Wouldn't make any sense to have a y there. Does that make sense? Everybody happy? Okay, so that's the process. We're going to do some more examples, but from this point, now that we have an iterated integral, plug and chug, right? I'll let y'all think through those details. A good exercise. Make sure to remember which variable is a constant, which variable is a variable, at what stage of the calculation. You got to make sure you can do that reliably. Okay, same region. Rectangle, same integral. The only thing that's different with this next example is we're going to slice the other way. Because we can. You always have two options of which way to slice. You can do dy dx like we just did. You can do dx dy that we're about to do now. Which one you should do depends on the circumstance. We'll talk later about how to make good decisions for which one of those to choose. Okay, so let's do it though. Let's talk about the y bounds. Well, y is going to go like that, and the y slices will look like this. And I think it's these outside bounds again are usually kind of freebies. Y pretty clearly starts here, where y is pretty clearly 0. Y is going to end, here, where y is basically given as 1, because again that point is given. Okay, so the outside bounds, very often the fish just jump in the boat. Let's think now about fixing a value of y. Now we're going to think about how x varies. There's going to be a lower bound for x and an upper bound for x. Again, we go through the process. The lower bound, still focused on x here, the lower bound for x comes from that point, which is on that curve, which we've already agreed has that equation. Now again, here's another common fumble on the 2-yard line. A lot of students mess this up. A lot of students will look at this and say, oh yeah, we've already solved, yeah, this is the one where you put x, because that's what it was on the previous page. But we're doing something different now. We're slicing in a different order. The variables are playing different roles. You've got to keep track of all of this. So now, at this stage, we're looking for an x bound. I need to know x as a function of y. I need to find the function of y that tells me what x is. So within here, I need to solve for x. This is the function of y that tells me what x will be. Y, then, is my lower bound. How are we doing? Does everybody see that? Okay. And then, analogously, you want to find the upper bound for x. The upper bound comes from that point That point is on that curve. That curve has that equation. Again, solving for x. Again, conveniently, kind of already solved for. X is 1. My upper bound for x is 1. Everybody see the process? Everybody happy? All right. I'm out of time anyway. Okay. Anyway, perfect stopping point. We will see some more examples and start addressing the question of how to make good decisions about which way to slice next time. Y'all have a good rest of your week. See you on Friday.